In section 5.4 we're working with vectors. Remember, vectors must have magnitude and direction. So the magnitude is our length, direction is our angle. And in the book, if you have heavy bold type, then that's when it's referring to a vector. If we have the arrow above, that's referring to a handwritten vector. Also with vectors we have our initial point, and that is where the vector begins. And then where it ends is our terminal point. And if we're talking about adding vectors, so if we have, here's vector v, and then here is vector w, then our resultant vector across here would be v plus w. And commutative property would hold true because if we have, this is our vector w, same magnitude, same direction, and here is vector v, we would have the same resulting vector. So the commutative property holds true. Associative property, if we have vector v and vector w and vector x, then we would know coming across here would be w plus x, and coming across this direction would be v plus w, and our resulting vector from here to here is going to be the same regardless of how we go, and that would be v plus w plus x. So the associative property also holds true for adding vectors. Now if we have a vector v here and here's vector w, again vector v, same magnitude, same direction. Here if I'm going back, same magnitude but the other direction, we would think of that as subtracting w, or the opposite of w, so that would be our resultant vector here we would refer to as v minus w. Here we're looking at properties if we are multiplying vectors by scalars, and what we're saying in each of these examples is that we have these variables, and in this we're referring to these variables as real numbers, and all of these properties would hold true. So that if we're going to multiply a vector by 0, then it's going to 0. And we already talked about -1, now that vector is going in the opposite direction. If we're multiplying by two different numbers, we can multiply by the vector, and in each case, and that will hold true however we do this with these properties. The magnitude of vectors will be shown symbolically here like this, and when we're talking about the magnitude, remember we're talking about the length of the vector. And we will always refer to the length of the vector as being positive, because length would be positive, and some different properties we have for the magnitude, just like we're saying here right off the bat. First thing is it's going to be a positive value. And so even if we have a negative scalar or -1, and we're going the opposite direction, the magnitude will still be a positive value. It'll be equal to 0 if and only if the vector is equal to 0. And even if we're multiplying by a number, when we talk about the magnitude, if that value is negative, then we'll take the absolute value of it. So if you have a vector and the magnitude is equal to 2, and so then if we're talking about -4 times that vector and the magnitude of that, we would take the absolute value of that scalar and then take that times our magnitude of the vector. So we take 4 times 2, so then that magnitude with this scalar would be 8. Also, if we're referring to a unit vector, unit would imply then that the magnitude of that vector is equal to 1. If we have vector v and its initial point is at the origin and it goes to point P, then we would refer to this as a position vector, and our components for the vector would be those points A and B. So those would be our components of vector v. Now, if we have a vector that does not start at the origin, if the initial point is not at the origin, so we have point 1 here, and now our vector is going from point 1 to point 2, we could still find the components. So we're saying that point 1 is the initial point, we have coordinates x1, y1, point 2 is our terminal point with coordinates x2, y2. We would say that this vector going from point 1 to point 2 would still be equal to the position vector, and we could find those components by finding the difference for those 2 points. So if we have equal vectors, we're saying that vector v has our given components and vector w has these components. They would be equal vectors if and only if those components are the same. So going back to our last example, we would say that as far as finding these components, the vector here, as far as our magnitude and direction, if we were to reposition this so it's a position vector, I know that to find these components where I'm taking x2 minus x1 and y2 minus y1, that's just going to shift point 1 here. But as far as the vector goes, we're still going to have the exact same magnitude and direction. So these would be parallel, despite how I'm drawing it here, where it's going to shift the exact same way for those 2 points. The magnitude and direction, the components of that vector would be the same. Those would be equal vectors. Now let's look at a vector in terms of its horizontal and vertical components. First of all, we're going to have our I unit vector on the x-axis going to be represented here, and that's our I component, and that would be 1 unit. And then j is going to be our vertical component here. And when we're talking about the vectors and then we have our I component and our j component, don't get the I here mixed up with in complex when we're talking about imaginary. We're talking about 2 different things there. And when we're writing this, we can write any vector in terms of these I and j components. So if we have A and B as the components here, A is the I component here, and then with the B, this is where we're referring to that j component. So we could rewrite this in terms, we could say that here is our I component, and here's our j component for that vector. So if we have our vector, and we have our component here, A1, that's our I component, and then B1 is our j component. So we could say that our components here are A1 and B1. And then we have vector W, and now we have our component here where we're going to say this is A2 and B2. So that means that we have our I component is that A2 value, and our j component is that B2 value. Now we have certain things that are possible. We've already been talking about the sum of vectors. If we have vector v plus vector w, what we can do then is we can take our components, A1 plus A2, that's an A, A2, we add those components. That's going to be our I component. And do the same thing with our B values with those j components, add those. And that's going to be our j component. And then our components then for the resultant vector, of course, would be A1 plus A2 and B1 plus B2 would be the components for the resultant vector there. If we're going to take the difference then we would subtract those components. So now I'm going to take a1 minus a2 for my I component, and I'm going to take b1 minus b2 for that j component. And again, the components there again would be now the difference in those. If we multiply by a scalar, then I would do the same thing to each of these components. So I'm going to take that scalar value, whatever that may be, times a, my I component, and take that same scalar value times b, which is our j component. And again, the components then there. And as far as the magnitude of our vector, to find that, we're going to take a squared plus b squared and take the square root of that value. Now if we're talking about vector v, then that would be our a1 and b1, because those are the components of vector v.